Welcome everyone in today's webinar on Ethernet 1600G, from terabits to reality. Over the next few minutes, we'll be touching the following topics. It contains TrueChip introduction, its P3 framework, Ethernet overview, the evolution of Ethernet, the introduction of 1.6T Ethernet, the unwavering need for 1.6T Ethernet, and we'll also discuss about the Ethernet verification IP overview, its block diagram, its features, its GUI, its test suites, and we'll also discuss one sanity test case, its waveform overview, and one sync header corrupt test case. First, let's start with an introduction of TrueChip solutions. TrueChip is a leading provider of verification IP solutions and design services. It follows a unique P3 framework of proven solution, perfect integration, and prompt support. It has direct sales and support presence across North America, Europe, and Asia, and it is having its R&D centers in India and Vietnam. It is a provider of VIPs like Ethernet, PCI, USB, storage, and many more VIPs. Next, before discussing 1.6T Ethernet, let's go over a Ethernet overview because it is the backbone of digital communication. Ethernet is a family of wired computer network technologies primarily used for local area networks and developed for standardizing how devices communicate. Ethernet was originally designed for wired connections, although its packet-centric approach and carrier-sense multiple access with collision detection establish a robust framework for data exchange across all interconnected devices. Ethernet was formally standardized by IEEE 802.3, ensuring its global coverage and widespread adoption. Ethernet was originally developed in early 1970s at Xerox PARC as a means to allow their Alto computers to communicate with each other. Ethernet protocol provides reliable, high-speed, and cost-effective data transmission, forming the backbone of modern networks. Its versatility allows it to be deployed across various physical media, from copper wires to fiber optics, supporting an immense range of applications from business communication to internet backbone infrastructure. Today, Ethernet is widely used everywhere, underpinning nearly all wired network communications, from the intricate connections within small offices and small homes to colossal server farms. Billions of devices now rely on Ethernet for faster, high-speed, reliable data transfer. Now, let's discuss about the evolution of Ethernet and how Ethernet grew over the years. From its modest beginnings, Ethernet has consistently pushed all the boundaries of data transmission, adapting to ever-increasing demands of the world. This graph below highlights the exponential growth in bandwidth requirements driven by data-intensive applications and the fundamental shift towards cloud-centric architectures. This graph here perfectly illustrates the rapid evolution of Ethernet over time. As you can see, the progression in 2002 to 100 Gbps in 2010 was steady. However, the growth curve has become much steeper in recent years. By 2017, we had 200 and 400G Ethernet, and now we are in the era of 800G with 1600G on the horizon. Moving forward, this brings us to the main topic, 1.6T Ethernet. The 1.6T Ethernet represents a monumental leap in networking capability. The standard builds on the advancements of 800G Ethernet to deliver unprecedented data rates for the most demanding applications. Its key characteristics include unprecedented bandwidth offering 1.6 terabits per second and advanced modulation, which uses higher order modulations like PAM4 to achieve high spectral efficiency. It also focuses on lane parallelism, exploring the configurations like 8 cross 200G or 4 cross 400G electrical interfaces to optimize port density and power efficiency. 1600G Ethernet is crucial for addressing the increasing traffic demands, which are driven by artificial intelligence, machine learning, cloud computing, and next-generation data center interconnects. Next, let's discuss that why even 1.60 Ethernet is useful. The demand for ever-increasing network bandwidth is not a luxury but a necessity. Driven by fundamental shifts in computer networking and user behavior, 1.60 Ethernet directly addresses these escalating requirements. The applications include hyperscale data centers, which involve rack-to-rack and cluster-to-cluster connectivity, artificial intelligence and machine learning, in which training large AI models require immense data transfers between GPUs. Next, many use cases relies on expanding cloud computing infrastructure and introduction of new technologies like metaverse, augmented reality, and high-quality video streaming. Another use case can be related to saving power and money by replacing multiple slower Ethernet connections with fast ones like 1.60. Now, we can move forward to explore 1.60 Ethernet verification IP, starting with an overview. 1.60 Ethernet verification IP is compliant with IEEE 802.3 2018 Clause 119 and the latest IEEE 802.3 DJ draft, ensuring that it is at the cutting edge of the standard. VIP is compatible with Mentor Questa, Cadence NC, and Synopsys VCS. It can be used in both standalone and SoC verification environments. The VIP supports all the types of error injections with its monitors and scoreboards, and it also supports on-the-fly protocol checking. VIP also provides a graphical protocol layer analyzer for easy debugging, which is an additional benefit. Now, let's see the block diagram of 1.60 Ethernet VIP. This diagram provides a high-level view of how 1.60 VIP operates. It shows the key layers including the MAC client, the reconciliation sublayer, the PCS, and the PMA. Each layer has its own monitor for protocol checking. In addition to the protocol checking, monitor also samples data from different interfaces in order to process and compare it. If it finds any mismatches, it flashes suitable errors and warnings. Meanwhile, the scoreboard is connected to both the instances of Ethernet to perform packet comparison. Moving forward, let's discuss some of the basic features of 1.60 Ethernet VIP. The 1.60 Ethernet VIP supports a standard 1.60 MI interface and two 800 Gbps PCS with Reed-Solomon encoding, and the encoding which is used here is 514 to 544. It supports 16 PCS lanes of 106.25 Gbps. The PMA of the VIP support 1:1 and 2:1 muxing with all possible widths for PCS to SerDes interface. The VIP supports RSFSC decoder with 15 symbol error correction capability. VIP has callback support in all layers to provide flexible control to the user. It also supports dynamic as well as error injection scenarios. VIP also has on-the-fly protocol checking features and also supports built-in coverage analysis. VIP also has graphical analyzer to show transactions for easy debugging. VIP's Mac support features like data payload framing, reassembly, FCS calculation, and data padding. Mac supports multiple types of frames like data, pause, queue tagged, VLAN tagged, jumbo frames, etc. And also, the Mac can be configured both for normal and error injection scenarios. It also has callbacks for complete user control. VIP's RS support all the features mentioned in Clause 81. It samples data from the standard PLS service interface and drives it onto the 1.60 MI interface. Then, it provides continuous 64-bit data and control over the transmit path and expects the same over the receive path. VIP supports Reed-Solomon encoding, decoding, and scrambling with 15 symbol correction. VIP supports alignment marker insertion and also the CDR operations on the data received from below sublayer. VIP PMA provides features like bit muxing, input lane data recovery and clock recovery, and tolerance to skew variation. VIP contains separate layered bus monitors for Mac, PCS, and PMA for easy to plug in capability and compliant with the standard specification. The monitors keep full information about each transaction and flashes appropriate errors and warnings in protocol violations. All the VIP monitors support functional coverage for all the configurations. The VIP scoreboard ensures data integrity and compares the transactions on master PLS interface to slave PLS interface. If it detects any mismatch, it logs it with appropriate error ID. Moving forward, let's discuss about Ethernet VIP GUI, that is known for its ease of debugging. The modern architecture of VIP uses GUI to make debugging easy and hassle-free. The GUI shows a detailed description of all the transactions, and it is also created for MMD transaction for easy debugging. GUI shows all the commands across time and is compatible with both Linux and Windows. Let's move forward to see a wide variety of test cases which Ethernet VIP offers. To ensure complete and robust verification, the VIP offers a comprehensive set of test cases. First is a basic and directed tests, which contain test cases for basic flow and functionality. Next is random and error injection tests. Random test cases are for complete functionality and corner case checks, while the error injection test cases are for deliberate error injection scenarios. Assertion and curve point tests ensures all assertions and curve points are met. Lastly, the user test suite, in which the user can write their own test cases by extending existing sequences or writing new ones to meet specific requirements. Now, let's move forward to discuss the quality of VIP which TrueChip offers. All TrueChip VIPs come with a comprehensive set of assertions, test plan, and coverage plans. VIP has directed test cases to achieve 100% functional coverage. All the VIPs have strong protocol checking monitors and are tested with all industry-leading simulators. VIPs are coded in System Verilog with UVM and are being used in productions by various customers. TrueChip has its own bug tracking system and provides on-site support for customers in India, and also provides support over bug tracker, calls, screen sharing, and VPN. Now, moving forward to the next slide for discussing a sanity test case. This slide provides a glimpse into a sanity test case and how VIP logs all the information. In the first screenshot, we can see a transmitter PCS collects 64-bit blocks from the MI interface and encodes them into 66-bit block. As it accumulates 4 66-bit block, it transports them into a 257-bit block, which goes through the Reed-Solomon encoding. Further, 20 such blocks make a 5140-bit block that gets further encoded into 5440-bit block. In the next screenshot, we can see that when each lane achieves alignment lock, then it is said that all alignment lock is done. Then when this happens, VIP logs all the information so that the user can know. Now, the next slide indicates one of the features of PCS interface. In the first screenshot, the PCS monitor compares the received data from the lower sublayer interfaces with the data it sampled from the MI interface. In the second screenshot file, inversely, the PCS monitor compares the transmitted data from the MI interface with the data sampled from the lower sublayer interfaces, example, the PMA interface. Now, in the next slide, we can see two screenshots of the waveform. The first screenshot is from the transmitter PCS, where we can see 4 66-bit blocks are collected to form a 257-bit block, and 4 257-bit blocks are collected to form a 10828-bit block. As we have two instances of PCS, this process of collecting 4 66-bit blocks and encoding it happens in a round-robin fashion, which Here, it is governed by round-robin distribution TX signal. In the next screenshot, we can observe that when all lanes are locked and de-skewed on the receiver side, then the alignment lock signal gets asserted. Now, heading towards the next slide, let's discuss about a sync header corruption test case. To show the power of error injection and monitoring features, this slide shows a test case where we intentionally corrupt sync headers while transmission. You can see that how the VIP logs all the appropriate warnings with their error IDs and corresponding spec sections. Additionally, it also provides a summary report with total number of packets transmitted and received, which is crucial for verifying data integrity. Now, that brings us to the end of the webinar. Thank you for your time and joining the webinar today.